All right, so in this video, we're going to kick off this year of calculus with trying to get to the heart of what we're going to study this year. And so my goal of this is to get you guys to kind of understand what this entire first unit is going to be about in terms of this idea of something called a limit. And I'll also introduce the idea of something called a derivative. At the end of this, we will do a very specific example of how to find a derivative methodically and as the year goes on, we'll learn some shortcuts for these things. We'll do the long way right now in order to help with some understanding. And then for homework tonight, you guys will have like a 3 or 4 question assignment that you'll try, and you'll finish it so you can turn it in when we get back to class next time I see you. So I want to start out with a scenario here. I want to see if we can determine some ways to figure out how fast we were moving at a particular instant in time. Okay, so I'm going to give us some information here. Let's say that I told you that at 5 o'clock we were 2 miles from TMI. Okay, and then at 6 o'clock, an hour later, we were 10 miles from TMI. Okay, and I'm going to pose the question here: how fast was I moving at 5:30 p.m.? Okay, how fast was I moving at 5:30 p.m.? All right, and I think if I gave this question to you guys, most of you guys would understand. I might not be able to figure out exactly how fast I was moving at 5:30 p.m. just with this information, but we could at least estimate it by figuring out what our average rate of change was from 5 o'clock to 6 o'clock. Okay, these are pretty good values because 5 o'clock and 6 o'clock are exactly evenly spaced from 5:30 p.m. So if I know exactly where I was at those 2 points, what I could do is I could just figure out how fast was I moving from 5 to 6, and maybe that's a pretty good estimate for exactly how fast I was going at 5:30. Okay, well if we wanted to do this, and let's say that we wanted to do this in miles per hour, we'll keep it simple since that's how it was presented to us. The way that we would find that average rate of change is, well, we would just do the change in miles. We went from 2 to 10, that's a change of 8 miles. And we went from 5 to 6 o'clock, that was a change of 1 hour, which means we were going 8 miles per hour. Okay. Now, is that the exact speed that I was moving or exactly how fast I was going at 5:30 p.m.? Who knows? Maybe, maybe not. I don't quite have enough information to do that, but this is probably the best estimate that I'm going to get from the information that was presented to me right here. Okay. So hopefully you kind of follow what I'm doing right there. My next question would be, is there a way that I could make this more accurate? Okay. So like how could we get more accurate here? Okay. Because remember, I'm trying to figure out exactly where we're at 5:30 p.m. Okay. I was only given data points right there at 5 o'clock and at 6 o'clock, but maybe if I get some other better data points, I could come up with a better estimation. Okay. So what if I then told you some more information that at 5:15, let's say I was 3 miles from TMI, and at 5:45, I was 9 miles from TMI. Okay. This information is a little bit better. It's a little bit more accurate because guess what? These points in time that I'm giving you, they're closer to 5:30 p.m. Okay, they're closer to 5:30 p.m. So they're probably going to give me a better estimate of exactly what was happening at 5:30. Because if I want to know exactly what was happening at 5:30, I want to get information that's as close as possible to that point in time. Okay, so let's try it. I'm going to go ahead and abbreviate here. AROC. If you ever see this, that means average rate of change. Let's do the same thing we did on the last problem. The change in miles from 9 to 3, or from 3 to 9. That's a change in 6 miles. Okay. And then the distance in time from 5:15 to 5:45, that's half an hour. Okay. When I divide by 0.5, that is the same thing as multiplying by 2. So this is like 6 times 2. And when I'm done, I get 12 miles per hour. Okay. And so we see here, we get a much higher answer than we got on the last one. But my guess would be this is probably a better estimate because we had points in time that were even closer, centered around 5:30. Okay. Now I want to continue this idea. Again, our goal here is to figure out exactly how fast we were going at 5:30. Not an estimate, not an average rate of change, but really we want to know what's the instantaneous rate of change at exactly 5:30. Okay, so I'm going to continue the question further. How could I be more accurate? Okay, how could I be more accurate? And I've had some students in the past where they've said, well, what if, Mr. Griffith, you just told me exactly where we were at 5:30? Okay, and I say, well, okay, I'll tell you exactly where we were at 5:30. Technically, we don't know if this is AM or PM, so we'll leave that ambiguous for now. But let's say I told you that at exactly 5:30 we were 5 miles from TMI. Okay. Now, if this is the only piece of information that I gave you, this is not going to be enough to figure out exactly how fast I was going at 5:30. This only tells me where I was at 5:30. Okay. But as long as we have something to compare this to, we might be able to get a pretty good estimate of where we were at. Okay. So let's think about it. I mean, if I knew that at 5:30 we were 5 miles from TMI, I could compare this to, I don't know, let's say 5:15. Okay. Well, average rate of change. From at 5:30 I was 5 miles. At 5:15 I was 3 miles. Going back up here, so that would be a change of 2 miles. And from 5:15 to 5:30, that's 15 minutes, which is a quarter of an hour. Okay. So if we think about this, 2 miles divided by 0.25 divided by 0.25 is the same as multiplying by 4. Okay, so 2 times 4. Now we go back to this estimate of 8 miles per hour. Okay, so which one's right? I don't know. Okay, again, I can't say definitively which one is even a better estimate right here. I'm thinking this is probably a better estimate, but I don't know exactly for sure because I don't know exactly what's happening at 5:30 p.m. Okay, and again, I want to continue this question. How could I be more and more and more accurate? Okay, because what I've got right here is one estimate when we were an hour apart. I've got another estimate when we had data points that were 30 minutes apart. I've got another estimate from a data point that included the actual position at the time we're looking for, and another data point that was a quarter of an hour apart. Okay. And so maybe you're starting to think, well, Mr. Griffith, if I want a really, really, really accurate estimate, maybe you can give me something at like, well, I don't know. What if I knew where he was at 5:29, and then I also knew where he was at 5:31? Would that be a pretty good estimate? Yeah, it probably would be better than looking at ones that were 15 or 30 or an hour away. But I would say, hey, can I become even more accurate? Yeah, maybe if I knew exactly where we were at 5:29 and exactly where we were at 5:30, which we already know, this might be even more accurate. Okay. Or what if we knew exactly where we were at 5:29.99 seconds and 5:30.01 seconds? Okay, that might give me something that's even more accurate. Okay, so maybe you're kind of tracking with what I'm saying here. What I'm saying is if we can push these data points as close together as possible, maybe we can get a really, really, really good estimate of what's happening at exactly that point in time. Okay, so I'm going to do a little illustration here because this is kind of, we want to be able to connect what we're talking about with what we see visually. So let's say that I had distance on this axis right here and I had time over here. Okay, and I'm going to kind of keep this ambiguous right now. I know I gave you some distances and times, but I think it's going to be helpful just to draw this out visually. So let's say you knew that whatever this point in time was, that's what our distance was, and whatever this point in time was, that's what our distance was. Okay, and I wanted to know, well, what's the average rate of change between those 2 points? Well, the average rate of change between these 2 points would look like this. Okay, that's what we calculated when we found the average rate of change from 5 o'clock to 6 o'clock. Okay, what we did was we did the change in y divided by the change in x. Okay, and when we were done, if y was in miles, which is a distance, and the x is in hours, which is what time is, then when we're done, if we found that slope of that line, we would have something that was in miles per hour. Okay. Now let's say that then we had some other points in time that were, I had one that was here and another one that was, let's say we had one that was here and then we had another one that was here. Okay. And if I find this slope, I get a different average rate of change. Okay. But maybe the thing that I was trying to find, or the actual speed that I was trying to find, was somewhere in here, okay? And so let's say that we had a continuous range of values right here. Go ahead, I'll graph this in yellow. What if that was the times and distances for all points in time over the course from 5 o'clock to 6 o'clock, and I wanted to know exactly how fast we were moving at just this point in time, okay? Well, what we can do, and kind of the heart of the idea that we're saying, is that what we're trying to do is we're trying to take these data points and push them as close as possible to this point right here as we can. And if we can do that, we're going to start to get more and more accurate estimations of exactly what's happening at that point, okay? So this is where some vocabulary comes into play. These lines that I've drawn right now that connect two different points on the line, okay, they have a very specific name in math, and especially in calculus. They are called secant lines, okay? Both this line and this line are called secant lines, okay? Get fancy with the colors here. Okay, those are called secant lines. All right, but what you're going to notice is as we push these points closer and closer together, okay, so let's say we were looking at two data points here, okay, I still have a secant line, okay, but what I'm really trying to do is I'm trying to figure out exactly what's happening just at this point, okay, and this is another name in math. As we push secant lines together and they get closer and closer to the point that we're trying to look at, what those secant lines turn into is a tangent line. Okay, and a tangent line is a line that touches a function in only one point. Okay, it's like we took a bunch of secant lines and we took all the points and we pushed them closer and closer and closer to that data point where we were trying to find the rate of change. And what happens is those points get so close that we then just touch the function at that one point in time. Okay, if we can find the slope of a tangent line, okay, then what we're doing is we're figuring out exactly how fast something is changing at a particular point in time. All right, now, there are some formulas that kind of go along with this, and you guys know these formulas because you guys know slope. Think about this, an average rate of change, okay? Miles per hour, for example. An average rate of change, all that is, I mentioned this up above, is a change in y divided by a change in x, okay? So let me give you a scenario here. Let's say that I wanted you to find the average rate of change between the point x, comma, f of x, and c, comma, f of c. Okay, average rate of change between x, comma, f of x, and c, comma, f of c. Well, when I find an average rate of change, all I'm doing is I'm finding a slope. Okay, so if I was going to find the slope between these 2 points right here, it would literally just be the change in y, which would be f of x minus f of c, divided by the change in x, which would be, in this case, x minus c. Okay, all this is just an expression for the slope between 2 points. Okay, that's what an average rate of change is. If I was to find the slope between any of these 2 points on the secant lines, I would be finding the average rate of change between those 2 points. Okay, but what I mentioned is if we want to find exactly how fast we're changing at just this point, we need to take all those all those points along the secant lines and push them closer and closer and closer to this data point. Okay, again, to try and illustrate, I'll do my best right here. Let's say we wanted to know how fast we were moving at just this point in time. Okay, well, what I could do is I could take that point, that box right there, and I could find the slope of the secant line between this point here and the point that I boxed. Okay, let's say, for example, that the point that I boxed here is c, comma, f of c, and then this point right here is x, comma, f of x. Okay, well, the slope of that line would give me the average rate of change between those 2 points. But if I wanted to make this more accurate, what I could do is I could try to move this point closer to the point in time that I'm looking at and then find that slope. And then I can make the points even closer together. And then I can make them even closer together and then make them even closer together and make them even closer together. And eventually what you would see is that secant line turns into a tangent line. Okay, now one thing that's important is we want to make sure we look at this from both sides. All right, so in this case, I looked at the points getting closer from the left. I would also want to look at the points getting closer from the right. But what you'll notice is as long as this is a nice smooth curve, sorry about that, as long as this is a nice smooth curve, whether I'm coming from the left or the right, I know this picture is a little bit messy, no matter what, this slope of the secant line starts to turn into the slope of that tangent line, okay? Which is just the slope of the line that touches the function in just that one point that we're trying to look at, okay? Now, here's the thing, and you guys know this from lower levels of math, the only number in the world that I can never divide by is 0, okay? I can't divide by 0, okay? And because of this, there's an issue with what I'm talking about, right? Because the whole goal is we're basically saying, if we can make the points as close as possible to this and find their slopes, we can find that rate of change. But the thing is we can't actually make those 2 points in the exact same spot, because think about this formula, okay? F of x minus f of c divided by x minus c, okay? If I made the point at x and the point at c in the exact same spot, well, what would happen is when I try to figure out the change in x would be 0, and I can't divide by 0, okay? So I actually can't do that where I push them completely to where they're in the exact same spot, because it brings up an issue mathematically with me not being able to divide by such a small number, all right? And so this is a very big concept and what we're going to spend the entire beginning of the year doing. I'm going to say, put this off to the side right here, to find an instantaneous rate of change, okay, which is quite a mouthful. So I'm just going to introduce this word now. We won't talk about it too much in this first unit, but we are talking about it today. To find an instantaneous rate of change, which is in calculus we call a derivative. Okay, what we need is something called, this is what our entire first unit is going to be, something called a limit. Okay, we need something called a limit. Okay, and so what a limit is it's a study of what happens as we get really close to a value without actually touching it. Okay, so in order to find an instantaneous rate of change, here's what we do. We take this formula for the slope between 2 points in time, and we take the limit as x approaches c. Okay, what does this mean? We'll talk more about limits as this unit goes on, but the limit as x approaches c means what we're going to do is we're going to see what happens as x gets really close to c. Okay, we're going to see what happens as x gets really close to c, which is exactly what we were doing right here. Here's where c was. I was taking x, and as I was drawing all these secant lines, I was trying to make x as close to c as possible in either direction. I was trying to make it as close to c as possible so that I could become the slope of that tangent line. Okay. Again, I'd like to emphasize the reason why x can't be exactly c is because if it was, if these were the same thing, when I subtract them, I would get 0, and I cannot divide by 0. Okay. So this is a very important formula that we will talk about a lot as the year goes on, whether we're talking about limits or we're talking about derivatives. Okay, but what I'd like to do right now is I would like to show you guys a full example of how we can use this formula to calculate the derivative of an actual function at an actual point in time. Okay, so we will conclude with this. I'm going to show you guys some calculator stuff on this problem. Okay, and then you guys can work on the practice. But again, this is what we're going to be doing this year. Calculus, I should really write this down. Calculus is the study, I should say, it's the mathematical study of change. Okay, so if we could break calculus down into a single sentence, what we're doing in calculus is we're trying to figure out exactly what's happening at a particular point in time. We're trying to figure out how much something is changing at one particular point in time. Okay, and so that's what we're talking about here when we talk about the difference between an average rate of change and trying to turn that into an instantaneous rate of change. And again, we need a limit to do this because in order to find a rate of change, you have to have 2 points in time. Okay, But in order to make it as instantaneous as possible, what we have to do is take points in time and push them as close as we possibly can, and then get a measurement of the rate of change between those 2 points in time. Okay, so let's look at this example right here. And like I said, we'll try this example, and then you guys will have some work to do for homework. So what if I ask you what's the instantaneous rate of change, or for right now, I'll also say the derivative of f of x equals x squared plus 4 at x equals 3. Okay, and for now, what I'd like to do, you don't necessarily have to do this, but I think it's good for you to get an understanding of what this looks like visually. Okay, so hopefully you guys remember from Algebra 2 and Pre-Calculus, if I was going to graph x squared plus 4, what that would be is, or what that would look like is a parabola. Okay, it would be a parabola that got shifted up 4 units. Doesn't have to be a perfect picture right here. But let's say that was our parabola. Now, x equals 3, that's right here. Okay, and we talked about an instantaneous rate of change. What that really is it's like the slope of the tangent line that just touches the function in this one spot. Okay, it just touches the function in this one spot. All right. So our job is to figure out the slope of this line, and the way that we're going to do that is we're going to try to come up with some sort of function that describes the slope between any 2 points on a secant line and the point at exactly x equals 3. Okay, so I'm just going to do a little experiment right here. We should be able to do this math. F of 3, if I go ahead and plug in f of 3 into this function, 3 squared is 9, and 9 plus 4 is 13. Okay, and let's just say, for example, we wanted to find the average rate of change between 1 and 3. So if I plugged in 1 into this function, 1 squared is 1, plus 4 is 5. Okay, so I'm just going to put a little note here, and we'll try this in just a moment. Okay, the average rate of change from x equals 1 to x equals 3 along this function is 13 minus 5, the change in y, divided by 3 minus 1, the change in x. So that would be 8 divided by 2. So the average rate of change from 1 to 3 is 4. Okay, again, this is sort of a side note. Okay, but my next question would be, can we come up with a function to determine the slopes of secant lines with x equals 3? Okay, so in other words, could I come up with some way to just describe the slope of any secant line if I pick an x value, and the slope of the secant line from that x value to the point at x equals 3? Okay, and I'm going to go back to this idea of an average rate of change. Okay, an average rate of change. And we should be able to do this if we'd like. Okay, because here's the thing. If I write down this formula right here, f of x minus f of c divided by x minus c, as long as I can plug some things in here, I can do this, okay? Because the point that we are concerned with right here is 3. So I'm going to go ahead and plug that in for c. Okay, and if I do f of 3, well, f of 3 is, we just determined this, 13. Okay, so I determined that right here. Okay, now the function itself, f of x, well, the function itself is x squared plus 4. All right, so I could go ahead and plug that in right there, and this should give me a formula for the average rate of change between any 2 points in time. Now we could obviously simplify this down a little bit. X squared, 4 minus 13 is minus 9, and this is x minus 3. And just check this out. So if I wanted to see if this formula works, let's say I wanted to find the average rate of change from x equals 1 to x equals 3. Okay, well, if I wanted to do this, what I would do is I would go to this expression that I've come up with, and I would plug in 1 for x. Now, we actually already calculated this ourselves. We said the answer should be 4. Let's see if this function that we came up with works. 1 squared minus 9, that's 1 minus 9 is negative 8. 1 minus 3 is negative 2. And I get this average rate of change of 4. Okay, so it seems like this function that I've come up with is working right here. It allowed me to find the average rate of change from, I could pick whatever I want for x right here, from that x value to x equals 3, I could plug it into this function for x, and it would give me the average rate of change between those 2 points in time. Okay. Now, here's the thing. We have this function. I'm going to go ahead and circle this. Our goal of this problem was not just to come up with this function, though. It was to find the derivative of the function at x equals 3. Okay, and remember, the derivative is the instantaneous rate of change, or taking a bunch of points that are close to 3 and pushing them as close as possible to 3 to see if we start to see something happening with the slopes of those secant lines and see if they're converging upon a particular value. Okay, again, as I draw this right here, if I take a bunch of slopes of secant lines and I make them closer and closer and closer to this point, eventually it's going to turn into the slope of a tangent line. Okay, so here's our goal, right? The derivative at x equals 3 can be found by taking the limit as x approaches 3 of this function that we've defined right here. Okay, it's found, again, I'll re-emphasize that it's found by taking the limit as x equals 3, as x approaches 3 of this function that we've defined right here. Okay, again, the way that you can read this is, hey, here's the formula for the slope between some point on the line and the point at x equals 3. That would be the average rate of change between those 2 points. It's the slope of a secant line. If I want to make this instantaneous, I'm going to take any point that I pick and make it as close as possible to 3 as I can. Can't actually make it 3 though, because if I did, 3 minus 3 is 0. Okay, now you look at that and you're like, man, how in the world am I going to evaluate this myself? Well, this is where a calculator comes into play. Okay, so I'm going to finish this problem by showing you how I would attempt to do this on a calculator. Okay, there are some algebraic ways to do this problem without a calculator, but for now we're just trying to understand the idea of a limit and how it needs to be used in order to find a derivative. So I'm going to show that to you right now. Okay, so here's what I want you to do. On a TI-84, okay, we will pull up y equals, and I'm going to plug in inside of here x squared minus 9 divided by, oops, sorry, let's close our parentheses here, divided by x minus 3. Okay, again, this is the formula for the average rate of change between any point on the line and the point at x equals 3. Okay, now what I'd like to do is I would like to set up a table that allows me to look at a bunch of points that are really, really close to 3 and getting closer and closer to 3 as we approach. Okay, so here's how I'm going to do that. It's important to know how to use a table on a calculator. I'm first of all going to press second in window, and where it says table set, this is going to allow me to set up my table. What I'd like to do right now is I would like to change the independent variable from auto to ask, and I encourage you to try this at your table with me. It'll make more sense as we go along. Okay. Once we turn that to ask, if you press second in table, what this is going to do is it's going to bring up a completely blank table. All right, this is where we get to pick some values that we want to test to see what's the slope of the secant line between this x value, whatever I choose, and the point at x equals 3. Okay, so let's say I started at 2. Okay, so what this tells me is if I found the point at x equals 2 and found the slope between that point and the point at x equals 3, the slope would be 5. Okay, but I don't want to be from 2 to 3. I want to get as close to 3 as possible. So maybe I try this at 2.5. Okay, and so we see the slope changing a little bit. And maybe let's try it at like 2.9. Okay, and then maybe we try this at 2.99. Okay, and then maybe we try this at 2.999. Okay, and it looks like this number is pretty obviously approaching a particular value. Okay, what I mean by that is this. We're looking at this half of the parabola. Here's the point where we're trying to find the instantaneous rate of change. What we just did is I started by finding the slope of this line, and then I moved this point a little bit closer and found the slope of this line. Then I moved this point a little bit closer and I found the slope of this line. And then I moved it a little bit closer and found the slope of this line. And what I did was I approached 3 from the left side. Okay, now you'll notice if I plug in exactly 3, it says error because I can't divide. I can't plug in 3 for x right here because it will make me divide by 0. Okay, so what I'd like to do is I just looked at this from the left side. We also want to make sure that we look at this from the right side. Okay, I like to start however far away when I plugged in this point. I want to be the exact same distance away when I plug in my next point. So maybe I try 3.001, and then the next point is 3.01. Okay, I'm just mirroring the distance between these points and 3 on either side. So now I'm going to be coming from the other side. Okay, 3.1. Look at that. I can try maybe 3.5, and then I can try 4. Okay, so what I'm doing right here is I'm looking at the slopes from the other side. So in other words, the first one, or the distance from, or the slope between 4 and 3 would be like this. And then the slope between 3.5 and 3 would be like this. And then the distance between 3.9, or the slope between 3.9 and 3, and 3.99 and, or 3.1 and 3, 3.01 and 3, 3.001 and 3. And what I'm doing right here is I'm making these points closer and closer and closer. And eventually you'll see that as I push those points, it becomes this tangent line right here. And the derivative is going to be whatever this slope approaches as we get closer and closer to 3. And what we can see right here, again, you can't plug in exactly 3, but it's fairly obvious that on either side of the point at 3, as we make those secant lines, as we push those points closer and closer together, that slope of the secant line starts to approach a value of 6. Okay, so what we would say here is the derivative of f of x. I'm going to put 3 dots here for therefore. Therefore, the derivative of f of x at x equals 3 is 6. Okay, remember, when we say derivative, we also mean the instantaneous rate of change. All right, so this video will be available to you. I'm going to go ahead and I will also put this chart in the notes. Okay, if you ever forget how to make one of these, this table, you can come and look at the end of this video because I know it's a pretty long video. But again, what we're looking at here is we're saying, hey, here's the slope as we approach 3 from one side. Here's the slope as we approach 3 from the other side. We can see that this slope is converging upon 6, so we can make a reasonable estimation that the derivative of the function at that point is 6. All right, your homework assignment, your teacher will have it, and it'll also be posted on Google Classroom. You guys have a wonderful rest of the day, and I will see you guys later this week.